today's stuff. We're going to go through a couple double angle formula examples, okay, and how we use those and apply those in varying ways. Going to use the double angle formulas to generate what we call the power reducing formulas, which are things that they're nice to have. Whether you use them a lot is another question, I guess, for debate. We're then going to use our double angle formulas to generate our half angle formulas. Okay, so that's kind of the plan for today. The plan for tomorrow then is to use our sum and difference formulas to generate what we call our sum to product or product to sum formulas. Now, lots of formulas, right? We go through what I've said. We've done the double angle. We're going to do half angle. We're going to do power reducing. We're going to do product to sum, and then sum to product. So there's 5 different categories of formulas here that we're trying to learn. But what is very, very, very important to understand is that all of them initially are generated by the sum and difference formulas, the addition and subtraction formulas. Okay, the sign of like s plus t is equal to sine of s cosine t plus cosine s sine t, that kind of thing. Does that make sense? So they all generate, or all have lines back to that set of 4, I guess 6 if you think about tangent as well. Those 6 initial sum and difference formulas we talked about last week. The double angle, the half angle, the power reducing formulas are all generated by, obviously, the double angles. Okay, obviously the double angle is generated by a double angle, or is addressed by it, but the half angle and the power reducing, you use the double angle formulas to create those. Okay, which the double angle formula then is the sum and difference formulas. Okay, so if I'm being asked to write sine of 2 times cosine inverse of x as an algebraic expression in terms of x, such that x falls between -1 and 1, how do we go about doing that? Okay, the first thing I think is important to note is that right there, we don't really have to deal with that and do anything with it. We just want to make sure that when we're done, we come back and look at that restriction and see if it makes sense to us on why the author wrote that. Okay, and maybe you would recognize why that has to be the case as well if you were to graph this thing. Okay, or if you kind of understand the domain for cosine inverse. Okay, so we'll talk about those things kind of as we complete the problem here. But initially, and it's always something that people struggle with, is that they attach a lot of times these conditions, and it's not something we have to directly focus on right now. Okay, so 2 cosine inverse of x. Remember what this is telling us. Whenever we use the inverse ratios, okay, what that, or ratio inverse functions, what that's providing us is an angle. Okay, now whatever that angle is, I'm not sure. We're going to have to draw a picture here in a moment. But remember that whenever you are being provided an angle, that means that that argument is a ratio of sides of my triangle, right? Does that make sense? Okay. And if it's a ratio that's using cosine, then it's the adjacent divided by hypotenuse, isn't it? So let's draw a picture of what this cosine inverse of x over 1 looks like. And I'm just going to make the argument that we should be in the first quadrant here. It just makes things a little bit simpler, sign-wise. So if I have cosine inverse of x over 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 That's what that's telling me, isn't it? It isn't that x over 1. If that's the adjacent side and that's the hypotenuse, then we are referring to that angle being this angle here that cosine inverse of x over 1 is providing. Does that make sense? Now, I don't know what that number is. I don't know what theta's numerical quantity is at the moment. But we do have the ability now to reference a particular angle. And if I have that angle, can I go through and find what this y value is here? Okay, and we'll talk about why we need to. Actually, let's actually readjust this or rewrite that, and then realize why we've got to figure out that y value right there. If I have sine of 2 cosine inverse of x, but we just found out that cosine inverse of x provides this theta, or evaluates to be that theta, then I could really write this as sine of 2 cosine inverse of x becomes the theta. Does that make sense? Okay. Now, that is our double angle, right? If you remember, the sine double angle formula from yesterday is 2 sine of theta cosine of theta. And now, if I look at the things I need for that formula to evaluate, I need cosine of theta, which we already have, right? Be x over 1. Okay? But I also need sine of theta, cursor disappeared. There we go. I also need sine of theta, which if I look at theta, sine of theta is going to be that side divided by hypotenuse, right? So I need to find this side in order to do that. So just using the Pythagorean theorem here, we should say that, so I'm going to call this, I'm going to call it A. So I'm going to say A squared plus x squared is equal to 1 squared. So then through the Pythagorean theorem, we should get A to be 1 minus x squared. So square root of 1 minus x squared. Now, can I evaluate this? Can I say 2? Now, sine of theta, what's sine of theta? Be that over that, right? And then times cosine of theta. Well, it's cosine of theta. It's adjacent divided by hypotenuse, right? And now the cleaner way of writing this would be to move the 2 and the x together. Now, y, so that's our finished product. We have created a algebraic expression in terms of just x, right? Why did that have to be true? Why did negative 1 is less than or equal to x is less than or equal to 1 have to be true? What happens if I put x to be 2 in there? That's terrible. Let me get rid of that. What if at that stage right there we put 2 in for x? What do you get underneath the radical? Negative 3, right? Can we take square root of negative 3? No. That gives us imaginary results. So that's what we're looking for. All right. Now, how do I know I'm right? Go to GeoGebra, go to Desmos, whatever you want to use. Type in sine of 2 arc cosine of x. Remember, arc cosine is simply just cosine inverse, right? gives us that curve. That's what we started with. We transformed it to look like 2x times the square root of 1 minus x squared. Is it the exact same curve? Look at arc cosine of x. What's the domain of that thing? Negative 1 to 1. Does that make sense then why this was here? This thing you can't evaluate this initial problem for things beyond negative 1 and 1. So that's why that's incorporated. Is that all right? Okay. So you see those every once in a while. Every once in a while I'll see when I'm providing people with like extra work for like the ACT or preparation for the ACT. These types of questions are kind of what they ask at the end of that ACT sometimes. They're trig questions, but a lot of them are, can we do our trigonometry with expressions and not so much numerical values? All right, so let's do another example. This is more of a numerical type of question. Let's say that we want to evaluate sine of 2 theta and cosine of 2 theta, where cosine of theta is equal to negative 2/5 and theta is in quadrant 2. Remember, evaluate means that we're going to, at the end, have a value, right? Okay. So, trying to find some numerical responses here. So, I'm going to write down my formulas for sine of 2 theta first. Sine of 2 theta, remember, is 2 sine theta cosine theta. Okay? The problem here, if I start using the information that provided me in the problem, I know cosine theta, right? Right there, I could replace that with negative 2/5. But I don't know that, right? And then the problem, that is not provided. But since you do know cosine of theta is negative 2/5, sine of theta is a known value, or it's an implied value. You just got to do a little digging to find it. Okay? So that's that formula. Then we also have our cosine double angle formulas, which you got 3 of them. Okay, you got those 3 to choose from, and we'll talk about those in a moment and why we would choose probably that one. But you can choose any one of them if you want to. Okay, let's evaluate sine of 2 theta. Now, like I said, if I start plugging things in, I don't know sine of theta, but I do know cosine is negative 2/5. So maybe I plug that in, and it allows me to visually recognize that I still need to find what sine of theta is. And the only way that I can find sine of theta is to draw a quick sketch. If we're in quadrant 2, so that's theta in quadrant 2. We've got a right triangle here. Cosine is negative 2/5. Okay. I'm now looking at this angle here, using the information from that angle to tell me something about theta. And I want to find sine of that red angle. don't I need that distance right there? How do I find that red distance? Pythagorean theorem. It's going to give you radical 21 when you do that, just to save a little bit of time for you. I think we all should be able to calculate that. So now what is sine of theta? Yeah, radical 21 over 5, cosine of theta, negative 2/5. So now, this is going to be, when I multiply across, what, negative 4 radical 21 all over 25. That is the sine of 2 theta. Okay. Now, we can check this. We can verify whether we've done this correctly. And I'm kind of cautious, kind of thinking about maybe do this all at the end once we find what cosine 2 theta is as well. But let's think about something else. Let's make sure that we've got that right, that negative correct, and see if this makes sense. If theta is in this quadrant right here, okay? So if theta is in quadrant 2, doesn't it mean that theta has to be between 90 degrees and 180 degrees? If it's in quadrant 2, does that make sense? So what would you do to all three parts if you rewrote this as 2 theta in the middle? Multiply that by 2, wouldn't you? Multiply that by 2. Is 2, so 2 theta right now, they're telling us that 2 sine of 2 theta should reside in one of those two quadrants, right? Is the sine value in those two quadrants negative? So that kind of validates that I've got that right sign. Does that kind of make sense? Not something I don't think you have to really pay attention to a lot or deal with a lot, but it is a concept to kind of understand and realize. And if you can get that right now with a double angle, we'll use the same thing a lot more often with the half angle. Okay, so now let's evaluate cosine of 2 theta. Now, let's be intelligent. Let's view this as maybe in the original problem they didn't ask me that. Let's do cosine of 2 theta like we were not asked to do sine of 2 theta, like we haven't done any of the picture stuff or anything like that. Okay. All they give me then is say evaluate cosine 2 theta, where cosine of theta is equal to negative 2/5. This formula here, I need sine and cosine, right? This one here, I need sine and only sine. This one here, I only need cosine. Does it make sense to use that formula there, provided this information? Does that make sense, everybody? Okay. So be thoughtful. Don't just arbitrarily just say, oh, this is the first one we learned, I'll use that one. Because if this is the only question being asked, and I use that one, I'm going to waste some time because I'm going to have to go to the side, draw a sketch, make a picture, all that kind of stuff, evaluate, probably use Pythagorean theorem to find a missing value, and that's time consuming. Where if they give me cosine, then I'm simply going to say that cosine of 2 theta is equal to 2. I'm going to write it this way. Cosine of theta squared minus 1. That's what that really means, right? What was cosine theta, though? Negative 2/5. Okay. So now this is going to become 2 times what? 4/25 minus 1. So it becomes 8/25 minus 25/25 gives me negative 17/25. 25ths. That's cosine of 2 theta. Okay? Didn't have to draw any pictures, right? What if the problem started off instead of giving me cosine of theta is equal to negative 2/5? What if the problem started off with said sine of theta is radical 21/5? You probably use that middle formula, right? Because in terms of the information they give you to work through the problem is in terms of sine, so you use the formula that uses sine. Right? If I ever use that top one, then I'm probably using it because they either started the problem off telling me what cosine theta and sine theta was, or I'm just going to kind of attack it brute force, not really caring what's more efficient or not. Draw a picture and evaluate. Okay? The thing is, you should be able to get that same result with the picture using, this formula or that first formula. It doesn't matter. Okay? But how do we determine if we're right? I mean, we did a lot of work there. It'd be really nice to know that these are accurate values. Okay? And what is also nice here is I just found that cosine of 2 theta was negative and the sine of 2 theta was negative. What quadrant is the cosine and the sine both negative? Third quadrant. So I know my 2 theta, whatever that angle is between 180 and 270 degrees. So let's go through some work here and see if that's accurate. If they give me that the cosine, is negative 2/5, right? Doesn't that mean that if I run negative 2/5 through that function, I should be able to find the angle? Let's do it in degrees. Does that kind of make sense? Is that all right with everybody? Okay. So then, if I double that, there's my angle. 227. That's 2 theta. That makes sense? So if I type in what cosine of that angle right there is, it gives me that number there, correct? Okay. I'm going to type in then, what was it, negative 17/25. Would you make the argument that those are pretty much the same thing? The only reason that they're not is because that number got rounded. Okay. Same thing happens with sine. If I want to find sine of 2 theta, now remembering that 227 is my 2 theta now. There's that. Okay. And I believe we had what? Over 25 or 5? Same values, right? Okay. Now, that 8 and that 9.3, not a big deal. Just a rounding issue. Does that make sense, everybody? Okay. But what we've done, Desmos, GeoGebra, whatever, they're putting in decimal format. They're doing rounding. We found absolutely no rounding. Okay, these are exact values. So those are some examples of how we use double angle formulas, why we use them, how they benefit us. Let's talk about a series of formulas.
In science, a formula is a concise way of expressing information.
I said series of formulas and Siri turned on. She's an idiot. Let's do power. Shut up! Power reducing formulas. All right. Power reducing formulas are exactly what they are, what they say they are. If we have powers like cosine to the 7x, or not cosine to the 7th of x, okay? We should be able to use these formulas here to dwindle that down so that I don't have any powers greater than 1. Okay? Thinking about exponents, okay, if we can minimize the size of our exponents, that's a nice thing, because exponents are hard to deal with sometimes, right? So minimizing them, bringing them down to ultimately 1 is like the overall goal. But to make them smaller or to reduce them is a useful task, okay? So like an example of this would be like if I have the expression sine squared x cosine, we'll do this example here in a little bit, but if I had that, can I rewrite that so that there are absolutely no powers of 2 for sine or cosine? Okay, that's what these formulas are going to allow us to do. Now, where do they come from? They're actually pretty easy to develop. They come from starting with the fact that cosine of 2 theta, both of these power reducing formulas come from your cosine double angle formulas. One of them comes from cosine double angle is equal to 1 minus 2 sine squared theta. And if you think about this, if I solve for sine squared theta, I should now have sine squared theta rewritten in terms of cosine to the first power. Does that make sense? So let's just take that equation. We'll subtract 1 from both sides. So it becomes negative 1 plus cosine of 2 theta is equal to negative 2 sine squared theta, right? Divide both sides by negative 2. So if I divide this by negative 2, it gives me 1. Divide this by negative 2, it becomes negative. And they're both divided by 2. So put them both over 2. And now we have a way of reducing a power of 2 so that we have a power of 1. That make sense? We do the exact same thing using cosine 2 theta, because there's another double angle formula for cosine 2 theta, and it's 2 cosine squared theta minus 1, right? Can I solve that for cosine squared? Cosine 2 theta plus 1 is equal to 2 cosine squared theta, divided by both sides by 2. Those are your 2 power reducing formulas for sine and cosine. What if I wanted tangent squared? Tangent squared is equal to sine squared divided by cosine squared, right? That's going to end up giving you 1 minus cosine 2 theta over 1 plus cosine 2 theta. Okay? Because the 2's are the common denominator, right? And a compound fraction. So I'm not going to write it out for you. I'm not going to deal with any examples today with the power reducing formula for tangent. But if you have sine and cosine, then you automatically have tangent through their division. So let's kind of work through this example here that is going to say, you know, obviously that's the problem we're going to start with, but it's going to say reduce or rewrite or simplify this expression. So let's just write it. Simplify sine squared x cosine squared x in terms of just cosine of x. So cosine of x is the only thing that I want to be left in our final result. If if we start making substitutions here, we now know sine squared x right there would be the same as 1 minus cosine 2 theta over 2. And we know cosine squared is this thing here. So I'm going to rewrite that. Now I'm just going to write it as, instead of cosine of 2 theta plus 1, I'm going to write it as 1 plus cosine of 2 theta. I think we'll see here in a moment why. So we can do that, right? That's nice because what did we just get rid of? I got powers of 2, right? Now we got to do some algebra, so we'll see if that really happened. But we got rid of sine, didn't we? Sine no longer exists. So we've kind of addressed that, that portion of the question said in terms of cosine. Okay. Now we should be able to do some algebra here. And when I do my algebra, what are that's a binomial, right? That's a binomial once it highlights. That's a binomial, right? What kind of binomials are they in comparison to one another? Say again? They're conjugates. So when I FOIL, 1 times 1, and now I get that as my numerator, and then I get 4 on the bottom, right? What stinks about that? Yeah, it brought back in a power of 2. We can fix that. We can address that. I'm going to rewrite this as 1/4. You don't have to. It makes it maybe a little bit more obvious. Oh, I'm sorry, and this should have been a 2 theta in there. So 2 theta up here, right, when we multiplied. So I'm just going to, basically rewrite each of those with that common denominator 4. Okay. Now here's the issue. We have another cosine squared here. Okay. Now think about this. And I'm going to use some concepts that we've seen in the past that might help us realize this a little bit better. We're going to do another substitution for cosine squared. So cosine squared down here, we're going to make this substitution here, right? Okay. But look at the relationships here. Okay. If I have in that identity on the right-hand side here, this is theta, right? Let's look better. No. It's just terrible. We've got theta over here, right? Okay. What does it turn into over here? 2 theta, right? It doubled itself, correct? What do you have right here? 2 theta. So this would be 2 theta. Does that make sense? So what would that become? 4 theta. Okay. I think maybe it's better to do this because we've done this before. Let u equal 2 theta. So would that thing look like 1/4 minus 1/4 cosine squared of u? And then you'll have 1/4 minus 1/4. Now, cosine squared u is exactly this. So I'm going to rewrite that as cosine 2u plus 1. I'm using u now instead of theta, but addressing it the same way. Does that make sense to everybody? Now, if u was 2 theta, can I put 2 theta back in right here? I have 2 times 2 theta. What's 2 times 2 theta? 4 theta. Okay? I think a lot of times it's overlooked on why that argument should change. A lot of people just want to keep it 2 theta throughout the entire problem. Okay? And you can't do that. All right, so we could probably maybe make this look a little bit better with distribute the negative 1/4 if we wanted to, so I could have like 1/4 minus cosine of 4 theta minus 1 all over 8 if we wanted to. That's terrible. All right, so this is our final answer. Because how do I know I'm done? And I can keep, I want to rewrite that many different ways using, maybe I go 1/4 minus cosine 4 theta over 8 minus 1/8. You can do that. If you want to come up with a common denominator of 8 and rewrite it all over 8, that's fine. You can do that. I'm just going to leave it there for the sake of saving a little time here. How can I determine if I'm right? And I guess I started inserting thetas instead of x's, but we started with x's, so they should have all been x's, or it doesn't really matter though. Can I type this in the a program? Desmos. So sine, what do we have? Squared x times cosine squared x. Does anybody know why it gives me that line right there? I think we talked about this. It's actually graphing the x-axis here, and it's incorrect. You want to be in radians. Because remember, it's trying to graph a distance against a distance, and when we're in degrees, it's not necessarily visualizing that as a distance. If I got that, now I'm going to, so that's what I started with, and I had powers of 2. Let's see if I have 1/4 minus cosine of, now it would be, x would be my input instead of theta, so 4x. Minus 1. Now I want all of that, so we gotta go back with some parentheses here. Over 8. And we've got an issue here. It is is it? Negative, so I'm putting that negative through cosine to negative 1/4, so negative 8. It's because of the way I type this negative in. That should be 1. Possible. If you, I don't know, because I think if I, maybe, yeah, okay, so that should be okay then if I do it that way. Nope, still doesn't. So when I wrote it by hand, I was distributing the negative through. I want to type it in that way. I don't maybe want to do that. It doesn't know what that is right there. Or, like I said, we could do this minus cosine of 4x, that over 8, minus then, what, 1/8? I can do it that way. Okay. If you want to make this, what, 2/8? Okay. And then, basically, I don't know if I can do this real quick, but condense also is 2 minus cosine of 4x minus 1. You could condense the 2 and the negative 1, put it all over 8, and get the same thing. Does that make sense? But the whole practice is what we start with that black curve produce the same thing as what we finished with. Okay. All right, so I want to briefly, those are power reducing formulas. If you remember what I said at the beginning of class, it's kind of a debate whether we're going to use those a lot. We don't use them a lot. Might be occasionally that you see it, that's a necessity. Ultimately, maybe when dealing with an equation that starts with sine squared in it, it might be easier to introduce what we just did with power reducing and get it down to a cosine to the first power type expression. But in the whole grand scheme of things, at least in this course, you don't use them all that often. The double angles you use a lot, and these guys are used a lot. And these are pretty straightforward, again, in their development. They come from the fact that cosine of 2 theta is equal to 1 minus 2 sine squared theta. And the other version of that, which says cosine of 2 theta is equal to 2 cosine squared theta minus 1. Okay? And if you think about our power reducing formulas came from these. And now our half angles are coming from them as well. But what we do here is we recognize that 2 theta and 1 theta, and then over here again, 2 theta and 1 theta, are they in a 1 to 2 relationship? All right. So we make a little bit of a substitution. We say let u equal 2 theta. Then u divided by 2 would equal what? Theta. Can you now, with those substitutions, can you put u right there? And can you put u over 2 right there? Are they still in a 2 to 1 relationship? So it's still my double angle formula. Does that make sense? Okay. So I get cosine of u is equal to 1 minus 2 sine squared of u over 2. It's still a true statement. This is still twice as big as that. But now what I can do is solve for sine of u over 2. If I solve for sine of u over 2, it provides me with my double angle. So I'm just going to go through kind of quick because we're running out of time here. Cosine u, I would subtract 1 from both sides. So I'm going to get that 1 to go away. I'll divide by a negative 2. So what that's going to look like, and I'm going to write it this way, dividing this by a negative would make that negative and that positive. Put it over 2, right? That would give me sine squared of u over 2. Is everybody following? You guys know how to solve for variables. So once I have sine squared isolated, what do I want to do to solve for sine? I'm going to take the square root. So we get sine of u over 2 is equal to the square root, so it's plus or minus, of this thing. And I'm going to rewrite it so it's 1 minus cosine of u all over 2. Might be important to say that plus or minus is determined by u over 2's quadrant, whatever quadrant u over 2 resides in. You do the same thing in solving for cosine of u over 2. So cosine of u over 2, and I'll leave this up for you to kind of prove to yourself, but cosine of u over 2 ends up being plus or minus 1 plus cosine of u over 2. My belief is trying to memorize. If you're in a course that forces you to memorize these, you do have reference sheets and stuff like that in this course, but I would not try to memorize those. because aren't they very similar to one another? The only thing that's different is the plus or minus sign. People are going to mess those up. Okay. I taught this class before. Rhodes kind of had its fingers in it. I didn't get reference sheets. Okay. People had to memorize it. And one of the biggest things they did was they mixed those plus or minus stuff. Now the benefit of this, okay, is now I can ask you the question: what is the sine of 22.5 degrees? Okay, because isn't that the same as saying the sine of 45 over 2? And 45 would be your u. Does that make sense? So now I can say plus or minus 1 minus cosine of u, but u was 45, all over 2. What's cosine of 45? So you get 1 minus radical 2 over 2, all over 2. Okay. Now, it's plus or minus, but 22.5 is in what quadrant? First quadrant. In first quadrant, the y value is positive. Okay. Now we can better write this, and hopefully, maybe we'll have time tomorrow to talk about it, but I think we should be able to do this math. This ends up being better evaluated at 1/2 2 minus root 2 all under the root. Okay. And that's just fraction work on the inside. And you cannot simplify that any further. You got a root under the root. It does not turn into a fourth root because there's subtraction there. You have a binomial underneath, and you cannot. Square root of square root is a fourth root, right? Okay. You can't do that here because of that subtraction. If you were to type in on your calculator, sine 22.5, and enter, it gives you a decimal. It's the same thing as 1/2 the square root of 2 minus the square root of 2. Okay. Obviously, so it's another ordered pair that we can start to memorize off the unit circle if we wanted to. Again, do we see it enough to memorize it? Probably not. These formulas are going to allow you to generate those quickly, okay, or more easily than your memorization. There is a 7-3 assignment on WebAssign. Make sure that you're looking at that, finish that up, and also that PDF I sent out on Thursday of last week. Make sure we're finishing that up. We'll make both those things due on. Or actually, I think I got the worksheet due on Thursday. And do I have WebAssign open until Friday? Anybody look at that? It's open until Friday. Okay. And Friday there's going to be a quiz. We'll talk tomorrow about a reference sheet for that quiz. How you too?
Homework assignment we haven't learned yet. It's like the half angle thing. It's like instead